Alright, so I wanted to do a little video so that we could possibly move at different paces depending on how much you need. So let's talk about this. Our linear relationships and the slope equation. This is on page 14 of the packet. A graph is linear when there is a constant rate of change. Constant rate of change is going to be our slope value, which we call m. Examples of linear equation. An example of linear equation that you'll see this year is f equals ma. We talked about this yesterday, just a little bit. And it just happens that the mass in this equation was the slope. So they happen to both be m's, and that's not always going to be the case, but that's a nice little parallel for us right there. And we saw that as the acceleration increased, our force increased. So up here, just a little graph of that. As our acceleration increased along this line, our force increased. And it always increased. If I increased my acceleration by 1, my force went up by, let's say, 2. And then I increased by another 1, my force increased by another 2. The slope-intercept form of a linear equation is just one way that people have chosen that they can describe this information. So our y value is equal to whatever our starting point is plus however much we have lifted. This lifted part is when we go over some, we know that every time we come over some, we will increase by the same amount because we have this constant rate of change. So the m is our slope, and when we multiply slope by the change in the value that's on our x-axis, we get some amount of change in our y value. So to figure out our final y value, you start with wherever you're starting. In this case, we started right at 0, but we could make a graph where we start at 2. So you could start at 2, and then you'd still increase by a certain amount. And you'd take your starting point plus how much you've lifted, and that's your y value. So in terms of calculating the slope itself, the common phrase that we use is rise over run, which tells us the change in y, or rise, change in y, rise, divided by our change in x, or our run. So that's why I always kind of draw these little squares here, because this right here tells me my change in y, and this right here tells me my change in x. I would say the most valuable thing you could do when you're trying to calculate slope is label it. Label it. So I'll start to come down and do this first problem with you guys. So the first thing I'm going to do is I'm going to call this point, I'm going to call it point 1. I'm going to switch colors over here, and in the green I'm going to have point 2. So that's going to help me when I start to use this formula over here. Now I can just plug numbers in, and I don't have to be as concerned about, did I use the right y value, or did I flip the x's and the y's? This way it can be a little bit more straightforward for us. So we'll have the slope is equal to y2, which is 11, minus y1, which is 7, all divided by x2, which is 0, minus sorry, color coding isn't my thing, and so I'm still getting used to it. X2 minus X1, which is 5. All right, and then we just do the calculation. So 11 minus 7 is 4, and 0 minus 5 is negative 5. So this is saying every time I rose by 4 units, I went to the left by 5 spaces. So sometimes I actually like to rewrite this the opposite way, so that I'm always describing when I move forward, what happens to y. So I'm going to rewrite this as instead a negative 4 divided by 5. So now every time I move to the right by 5 spaces, I go down by 4 spaces. So let's see if we can jump ahead to this example right here, and then we'll kind of bounce back and forth so we start to kind of see what the graph looks like. This is not the same problem as this one, but it's something that I want to be able to let you guys actually see something. So, right here, our first step is going to be labeling 2 points. So, I'm going to label that point right there because it went nicely through this 0, 4. And then where's another good point? That's kind of not on any lines, but this one is very nice. Ooh, I should do that in a different color. This one is very nice. And so if we have a graph like this already, if we have a graph like that already, we can actually just kind of start to count out the slope instead of having to do the formula. But the formula also works, so I'll show you both. So our rise, or let's start with our run. We're starting here. We go over 2, 4, 6, 8. So our run is 8. And again, we started with this point over here, so we have to start from here again. So now our rise, that's air quotes, our rise is negative 4. And the time that it took us to go to 8, we had to drop by negative 4. So that's negative 4. That's a fraction that I can simplify. So that's equal to negative 1/2. These are describing the exact same thing. It's saying that every time I go over 2, I go down 1. So I could know right there that this is at point y equals 3, because we've gone over 2, and that means that we must have gone down by 1. Just to show you that the formula does always work, I also want to show you that. So I'll write out these points right here. So this point is 0, 4. And I'm going to label that 1. And this point is 8, 0. So we're going to use this y2 minus y1 divided by x2 minus x1, so I'll write that out. y2 x2 minus y1 and x1. So we start to plug those in. Our y2 was 0. Our x2 was, oh, I'm sorry, I misspoke. Our x2 is 8. Subtract from that y1, which is 4, and x1, which is 0. So that'll give us negative 4 divided by 8, which again, we could, negative 4 divided by 8, which again is the same slope that we got by just looking at it. All right, so now I would like, zoom this out a little bit, on your own, how about you try to figure out BC and BC? And feel free to ask a classmate, work together. But I want to make sure that you guys have practice, because practice is really where we get strong with these skills. Very good.